Welcome you in the lecture series of random processes, detection and estimation. It is the 10th lecture of this series. In the previous lecture, we have discussed about the objective of the signal detection and parameter estimation, where we have studied about why the need of detection and estimation, formulation of signal detection and signal parameter estimation, difference between detection and estimation. In this lecture, we will discuss about the detection theory. The outline of this lecture are introduction. And the hypothesis testing is of three types: simple hypothesis testing, multiple hypothesis testing, and composite hypothesis testing. So in this lecture we will discuss about the simple hypothesis testing, which is Neyman-Pearson decision rule, Bayesian risk and Bayesian detector, the maximum likelihood detector, the map detector, maximum a posteriori detector. And in this lecture we will concentrate only the Neyman-Pearson decision rule. And the objective of this lecture, you will able to explain the difference between parametric detection and non-parametric detection, how Neyman-Pearson decision rule is used to detect deterministic signal. Now let us start with the introduction. A detection problem can be classified into two classes: parametric detection. In the parametric detection, the probability density function of the data is known, and in non-parametric detection, where the PDF of the data is unknown. The parametric detection can be of three types. First is simple hypothesis testing, where the PDF of each assumed hypothesis is completely known. In this, only two hypotheses are given. And second one is the multiple hypothesis testing, where more than two hypotheses are given and we have to choose one of them. And third one is the composite hypothesis testing, where the complete knowledge about the PDF of the hypothesis is not available. And the parametric detection can be of two types: Neyman-Pearson based and the Bayesian approach based. In the Neyman-Pearson based, when the signal is deterministic and it is non-random, and when the signal is assumed to be random in nature, then this is known as the Bayesian approach. So we will use the Bayesian approach for this parametric detection. So now we will start with the simple hypothesis testing. In simple hypothesis testing, we have null hypothesis H0, which indicate that there is no change from usual, and alternate hypothesis H1 indicates that there is change. So for example, in radar signal detection, H0 belongs to the target is present, and the hypothesis H1 corresponds to the target is present, and the objective is to decide which one of these hypotheses is true based on the observed data. In simple hypothesis testing, the PDF of each assumed hypothesis is completely known. In classical detection approach or parametric detection approach, this is based on Neyman-Pearson theorem, and the Bayesian approach, which is based on the minimization of the base risk. So now first we will start with the Neyman-Pearson decision rule. Suppose we have observed the random variable whose PDF is either normal distribution with 0 mean and variance 1, and normal distribution with mean 1 and variance 1. So two hypotheses corresponds to these two PDFs will be the hypothesis H0 will be when mean is 0, and hypothesis H1 corresponds to when mean is 1. And here we have to decide whether mu is equal to 0 or mu is equal to 1 is present based on the signal observation X0. And this hypothesis is known as binary hypothesis testing, where H0 refers to the null hypothesis and H1 is the alternate hypothesis. And the PDF under such hypothesis along with the probability of the hypothesis testing error is in this figure. And this is the null hypothesis, means the probability of observed data when H0 is given, and this is the probability of observed data when H1 is given, and this is the threshold 1/2. And so when the observed sample X0 is greater than 1/2, this means the probability of X0 when H1 is given greater than the probability of X0 when H1 is given. So the hypothesis H1 will be decided here if the observed data X0 is greater than 1/2. So here we compare the observed data with the threshold, and this shaded region denotes the type first error, and or you can represent it as P1 or the false alarm, means the probability of deciding H1 when H0 is true, and this shaded region is the type second error, means the probability of misalarm, and this is the probability of deciding H0 when H1 is true. The terms type first and type second errors are used in a statistical domain, but in engineering domain, these errors are referred to as false alarm or mistarget respectively. These two errors are unavoidable to some extent, but may not be treated off against each other. To do this, we need to change some threshold. The type first error probability means the probability of selecting hypothesis H1 when H1 is true is decreased at the expense of increase the type second error PM, means probability of selecting H0 when H1 is true. It is not possible to reduce both errors simultaneously. A typical approach is to hold one error probability value fixed while minimizing the other probability error. So for example, if we falsely say that an enemy aircraft is present, we may initiate an attack. To design an optimum detector, we want to minimize the error, means this probability of mistarget, we want to minimize this error, or equivalently to maximize this 1 minus probability H0 when H1 is true. So deciding the probability of H1 when H1 is true is the probability of detection, and the goal of Neyman-Pearson approach is to choose the one that maximizes the probability of signal detection. So the probability of false alarm will be the probability of selecting H1 when H0 is true, means the probability of the observed data when it is greater than threshold gamma, and given that H0 hypothesis is true, so it will be equal to integration gamma is to infinity, means the region R1, and because here the region R1 is from gamma to infinity, from threshold to the infinity. So we have integrated with the region R1 when H0 is true. So integration from gamma to infinity 1 upon under root 2 pi e to the power minus x square by 2 dx, and it will be 1 minus phi gamma, and this is the cumulative distribution function, and we have already discussed about this in the table of cumulative distribution function. How can we calculate this? And this is in the q function form, it can be the q gamma, and is in the q function form, and in the complementary error function form it will be equal to the 1/2 ERFC gamma by under root 2. And the probability of detection will be, means the probability of deciding H1 when H1 is true. So here the region R1, and it is from gamma to infinity, So this is the reason R1. So we have to integrate from gamma to infinity 1 upon under root 2 pi e to the power minus x minus 1 whole square upon 2 x minus 1 because h1 is 2. So uh, with this there is mean 1, and it will be 1 minus phi gamma minus 1, again the cumulative distribution function, and in the form of q function you can write it as q gamma minus 1, and in the form of complementary error function it will be 1 by 2 ERFC gamma minus 1 by under root 2. So the probability of detection will be the integration with the region R1 where this critical region lie of the PDF when H1 is true, and this is known as the power of the test. And the probability of false alarm means H0 is true, but we have take the decision in favor of H1, means we have taken the integration in the critical region, means we have taken the integration in the region R1, and this is known as alpha size of the test. Now Neyman-Pearson theorem. The NP theorem tells us how to choose R1 if we are given probability x h0 and probability x h1, means we have given the PDF under hypothesis h0 and h1, and we have to choose the region R1. So to maximize the PD, probability of detection, for a given probability of false alarm is equal to alpha, we decide h1 or h0 if this probability, this PDF under h1 hypothesis h1 divided by the PDF under hypothesis h2 will be greater than equal to the threshold gamma. So when this ratio is greater than gamma, then we will decide h1 hypothesis h1, and if this ratio will be less than gamma, then we will decide h0. Here this ratio is known as likelihood ratio, and this test is known as likelihood ratio test. And the value of threshold gamma is obtained from the probability of false alarm, and you know the probability of false alarm integration in the region critical region R1, the PDF under hypothesis h0, and it is given alpha. Now consider an example. In simple binary communication system, one possible signal observation is x0 and two hypotheses are hypothesis h0 corresponds to x0 is equal to omega naught, means only noise is present in the hypothesis h0, and in the hypothesis h1 it is corresponds to x0, it is equal to 1 plus omega naught, means the DC signal is present in presence of noise in the hypothesis h1, and where omega naught is the zero mean normal random variable with variance sigma square. You have to find the threshold value with NP test if the probability of false alarm is 10 to the power minus 3. So to find the threshold value, you know the PDF under the random variable x under each hypothesis. So under hypothesis h1 the PDF will be 1 upon under root 2 pi e to the power minus x naught minus 1 whole square upon 2, and under hypothesis h0 the PDF of the observation it will be 1 upon under root 2 pi e to the power minus x square naught by 2. So the likelihood ratio test will be Lx, it will be probability x naught when h1 true divided by the PDF of the PDF under hypothesis h1 greater than equal to gamma. So it will be 1 upon under root 2 pi e to the power minus x naught minus 1 whole square by 2 divided by 1 by under root 2 pi e to the power minus x square by 2 greater than equal to gamma. So after solving this we will get e to the power minus 1 by 2 x naught square minus 2x naught plus 1 minus x naught square greater than equal to this threshold gamma. So after solving this, we will get e to the power x naught minus 1 by 2 greater than equal to the threshold gamma. And taking natural log, you will get x naught minus 1 by 2 greater than equal to log e gamma. And you can write here as x naught greater than equal to 1 by 2 plus log e gamma, and this is the new threshold. 1 by 2 log e gamma will be gamma dash. So the critical region R1 will be the observed data x naught such that the observation is greater than gamma dash. So we will decide the hypothesis H1 or the critical region R1 in this case when the observation is greater than this new threshold gamma dash. And you know the probability of false alarm means the probability of deciding H1 when H0 is true, and this is given as 10 to the power minus 3. So you can write the probability of false alarm means probability of observation greater than gamma threshold when H0 is true. This is gamma dash, and so this means it is equal to the integration in the critical region R1 and the PDF of the under hypothesis H0. So it will be integration. The region R1 is greater than gamma dash, means gamma dash to infinity. So integration from gamma dash to infinity 1 upon under root 2 pi is to the power minus x0 square by 2, and this PDF is 10 is to the power minus 3. So this is equal to 1 minus cumulative distribution function phi gamma dash, and is 10 is to the power minus 3, and it will be phi gamma dash will be equal to 0.999, and from the cumulative distribution table the gamma dash will be, you can see here, the gamma dash will be approximately 3. So the value of the new threshold gamma dash is 3. So from this we can conclude that we decide H1 if the observed sample x0 is greater than 3. And so NP test is the observed sample greater than equal to 3. This means when the observed sample is greater than 3, we decide hypothesis H1, and when the observed sample is less than 3, we decide the hypothesis H0. And the probability of detection is the PD. It is equal to the probability of x0 greater than 3 when H1 is true. So it will be equal to because the observation is greater than 3, this means from 3 to infinity, and the PDF under hypothesis H1 is 1 upon under root 2 pi is to the power minus x0 minus 1 whole square by 2 dx, and this is equal to 1 minus 3 minus 1, and it will be equal to 1 minus phi 2, and this from the table you can see the phi 2 means the value is 0.97225. So you can write here, and you can find the probability of detection is 0.023, and you can see the detection performance is very poor in this case when the probability of false alarm is 10 is to the power minus 3. So the second part is perform the NP test to increase the detection performance. So you know, let consider the probability of false alarm is 0.5, and you know the probability of false alarm is from gamma dash to infinity integration 1 upon root 2 pi is to the power minus x square by 2 dx, and this is you have considered 0.5. So from this you will get it is 1 minus phi gamma dash from the definition of the cumulative distribution function, and it is 0.5. So phi gamma dash is equal to 0.5, and from that table the value of gamma dash will be 0, and so the probability of detection, it will be the integration from gamma dash to infinity 1 upon under root 2 pi is to the power minus x naught minus 1 whole square by 2. This means the PDF under hypothesis h naught, and it will be equal to, because the gamma dash value of gamma dash is 0, so it will be from 0 to infinity 1 upon under root 2 pi is to the power minus x naught minus 1 whole square by 2 dx. And from the definition, it is 1 minus phi minus 1, and it will be equal to 1 minus because you know phi minus x is equal to 1 minus phi x, and it is 1 minus phi 1. So you have the value phi 1, and from the table the value of probability of detection will be 0.84. So the probability of detection increased by increasing the probability of false alarm from 10 is to the power minus 3 to 0.5. Now consider the two hypotheses h naught. This is corresponds to xn, which is equal to omega n, means only noise is present in correspond to the hypothesis h naught, and in corresponds to hypothesis h1, xn is equal to sn plus omega n, where n is equal to 0, 1, 2, 3. This is the signal in presence of noise, where sn is equal to a for a greater than 0, and omega n is the white Gaussian noise with mean 0 and variance sigma square. So the question is, find the probability of detection. So first of all, this test problem is the test of a mean of multivariate Gaussian PDF. So in the hypothesis h naught, mu is equal to 0, mean is 0, and with hypothesis h1, mu is equal to a into 1. This is the matrix A for S1, S2, Sn, and A is the matrix for all ones. And or you can say that h naught will be the random variable x, the observed data x, which is the Gaussian PDF with mean 0 and variance sigma square I, and the in the hypothesis h naught, it will be the normal random variable with mean a into 1 and variance sigma square into I. So now the likelihood ratio test will be the PDF under hypothesis h1 divided by PDF under hypothesis h naught greater than equal to the threshold gamma. This means if this likelihood function is greater than gamma, then we will decide h1, and if this likelihood function is less than the threshold gamma, then we will decide hypothesis h naught. So, and you know the PDF under hypothesis h1, it will be the product of all the PDFs, because there are multivariate random variable x0, x1, x2. So the pi and 0 to n minus 1 upon under root 2 pi sigma is to the power minus xn minus a whole square upon 2 sigma square. So in this case, it will be 1 upon under root 2 pi n by 2 gamma is to the power sigma is to the power n is to the power minus 1 upon 2 sigma square summation n 0 to n minus 1 xn minus a whole square. And the PDF under hypothesis h naught, it will be pi n 0 to n minus 1 upon under root 2 pi sigma is to the power minus x square minus n upon 2 sigma square, and it will be equal to 1 upon 2 pi is to the power n by 2 gamma is to the power n is to the power minus 1 upon under root 2 pi sigma n 0 to n minus 1 x square n. So the likelihood ratio will be is to the power minus 1 by 2 sigma square summation n 0 to n minus 1 xn minus a whole square divided by is to the power minus x 2 sigma square summation n 0 to n minus 1 x square n, and this likelihood ratio will be less than equal to threshold. So I can write this expression as e to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n plus a square minus 2a x n minus x square n greater than equal to the threshold value gamma. So I can write this as e to the power minus 1 by 2 sigma square minus 2a n0 to n minus 1 xn plus na whole square greater than equal to the threshold value gamma. So taking the natural log both sides, you will get, so we will get 1 upon under root 2 pi sigma square minus 2a summation n0 to n minus 1 xn plus na whole square, and it is log 2 pi is log e gamma, and when this value is greater than this log e gamma, we will decide h1, and this expression is less than log e gamma, then we will decide the hypothesis h0. So I can write it as a by sigma square summation n0 to n minus 1 xn greater than less than h1 h0 log e gamma plus na square upon 2 sigma square, and so I can write it as 1 by n summation n0 to n minus 1 xn greater than less than sigma square by na log e gamma plus a by 2, and this is new threshold value gamma dash. So, and this is known as the sample mean, so the NP detector compare the sample mean to the new threshold gamma dash. If the estimate is larger and positive, then the signal is probably present. Now, to determine the detection performance, the mean and variance of the sample mean are the mean under hypothesis h0, it is equal to the expected value 1 upon n summation n0 to n minus 1 omega n, because under hypothesis h0 only noise is present, so it will be 1 upon n summation n0 to n minus 1 expected value of this noise omega n, and it is 0, the expected value of noise, the mean of the noise is 0, it is given, and the expected value under hypothesis h1, it will be expected value of 1 upon n summation n0 to n minus 1 sn plus omega n. Here in the under hypothesis h1, the signal sn is present with the noise, so it will be 1 upon n summation n0 to n minus 1 a, because the mean of the noise is 0 and the mean of this is a, and it will be equal to a. And the variance under hypothesis h0, it will be the variance of 1 by n summation n0 to n minus 1 omega n, and it is equal to 1 upon n square summation n0 to n minus 1 variance of this noise omega n, and it will be, the variance of the noise is sigma square, so the value of the variance under hypothesis h0 is sigma square by n, and the variance under hypothesis h1, it will be the sigma square by n again. So the under hypothesis h0, the sample mean having the normal Gaussian random variable with mean 0 and variance sigma square by n, and under hypothesis h1, this sample mean having the PDF, normal PDF with mean a and variance sigma square by n. So here the variance are same and mean are different. So, and the probability of false alarm means the probability of the sample mean greater than gamma dash when hypothesis h0 is given. So this means the integration from gamma dash to infinity 1 upon under root 2 pi, and it is because variance is sigma square by n, so under root sigma square by n e to the power of minus n x square upon 2 sigma square dx, and it will be, I can write it as gamma dash integration from gamma dash by and root sigma square by n to infinity 1 upon under root 2 pi e to the power minus xi square d xi, and from the definition I can write it as 1 minus phi gamma dash upon and root sigma square by n, and it will be from the, and in the q function form it will be q gamma dash upon and root gamma square and root sigma square by n, and in the complementary error function it can be written as 1 upon under root 1 by 2 ERFC gamma dash divided by under root 2 sigma square by n, and from this function q I can find out the threshold gamma dash as under root sigma square by n q inverse probability of false alarm. And the probability of detection means the probability of a sample mean greater than gamma dash when the hypothesis h1 is true. So it will be the integration from gamma dash to infinity 1 upon under root 2 pi under root sigma square by n is to the power minus xa whole square by 2 sigma square by n dx, and it will be integration from gamma dash minus a by under root sigma square by n to infinity 1 by 2 pi under root 2 pi is to the power minus xi square by 2 xi, and from the definition it will be 1 minus phi gamma dash minus a divided by under root sigma square by n, and in the q function form it will be q gamma dash minus a upon under root sigma square by n, and in the complementary error function it will be 1 by 2 pi ERFC gamma dash minus a upon under root 2 sigma square by n, and from this q function you can find out the probability of detection will be after putting the value of gamma dash as we have observed in the previous slide. So it will be probability of detection will be q sigma square by n under root sigma square by n q inverse probability of false alarm minus a upon under root sigma square by n, or I can write probability of detection it will be q inverse pf minus under root na square upon sigma square. So the probability of detection is q inverse probability of false alarm minus under root na square upon sigma square. So for the given pf the detection performance increase with the na square by sigma square, which is energy to noise ratio ENR. So this is energy to noise ratio. I can write in the terms of energy to noise ratio. The probability of detection will be q inverse probability of false alarm minus under root ENR. And if I sketch the curve between probability of detection and the energy to noise ratio, you can see that as the energy to noise ratio increased, the probability of detection increased. And here also the probability of detection increased with increasing the probability of false alarm. It is the increasing probability of false alarm. So we can see here that the probability of detection increased with increasing the energy to noise ratio, or you can and also increase with increasing the probability of false alarm. Now we will discuss the mean shifted Gauss-Gauss detection problem. In this class of detection problem, we observe the value of test statistics x bar and we decide h1 if x bar is greater than gamma dash, or you can say the x bar in under hypothesis h naught will have the normal random variable with mean mu naught and variance sigma square by n, and under hypothesis h1 it will be the normal PDF with mean mu1 and variance sigma square by n. Here we have to decide between the two hypotheses that differ by a shift in the mean of the x bar. So for this type of detection, the detection performance can be characterized by the deflection coefficient d square, and where d is approximately under root n mu by sigma. It is the distance between the mean of the PDFs under two hypotheses, and so the deflection coefficient can be expressed as the x mean, the difference between the mean under hypothesis h1 and under hypothesis h0 whole square by variance under hypothesis h0. So it will be mu1 minus mu0 whole square upon sigma square by n. And this is known this deflection coefficient d square is known as the signal to noise ratio, and the probability of false alarm means the probability of x bar greater than gamma dash when hypothesis h0 is true. So from the previous slide you can see this is q gamma dash minus mu naught upon under root sigma square by n, and from this you can calculate the threshold gamma dash. It will be equal to under root sigma square by n q inverse probability of false alarm plus mu naught. And the probability of detection, it will be the probability of x bar greater than gamma dash when h1 is true. This means the q function gamma dash minus mu1 upon sigma square by n, and here it will be after putting the value of gamma dash. So we'll get q sigma square by n q inverse pf plus q naught minus plus mu naught minus mu1 upon under root sigma square by n. So I can write it as q inverse pf minus mu naught minus mu1 upon under root sigma square by n. So the probability of detection, it will be q inverse probability of false alarm minus d square, the deflection coefficient. It is the deflection coefficient. So now the change in variance. Previously we have considered the change in the mean value and variance was there same. In this time we consider the change in the variance. Let xn n is 0, 1 to n minus 1 are independent identically distributed samples. We observe xn and assume under hypothesis h1 h0 xn is the PDF with mean 0 and variance sigma naught square, and under hypothesis h1 xn is the xn having the PDF with mean 0 and variance sigma 1 square. Here the mean are same and variance are different. In the previous case the mean was same and the mean were different and the variance was same, and in this case here sigma 1 square is greater than sigma naught square. Now the NP test decide h1 or h0 if the likelihood function Lx means the ratio of the PDF under hypothesis h1 and the PDF under hypothesis h0 will be greater than or less than the threshold value gamma. So if this likelihood function is greater than gamma, then we will decide h1, and if this likelihood function is less than gamma, then we will decide h0. So I can write the PDF under hypothesis h1 and h0. We will get 1 upon 2 pi is to the power n by 2 1 by sigma 1 is to the power n is to the power minus 1 by 2 sigma 1 square summation n 0 to n minus 1 x square, and divided by 1 by 2 pi is to the power n by 2 1 by sigma naught is to the power n is to the power minus 1 by 2 sigma naught square summation n 0 to n minus 1 x square, n greater than less than the threshold value gamma. And you can see from here the mean is same but variance is different for these two PDFs or for these two hypotheses. After taking the anti-law of this expression, we will get minus 1 by 2 1 by sigma 1 square minus 1 by sigma naught square summation n 0 to n minus 1 x square, n greater than less than log e gamma plus n by 2 log e sigma 1 square by sigma naught square. And You know, sigma 1 square is greater than sigma naught square. It is given, so I can write this expression as 1 by n summation n0 to n minus 1 sigma square n, greater than less than 2 by n log e gamma plus log e sigma 1 square by sigma naught square divided by 1 by sigma 1 square minus 1 by sigma naught square. And this is new threshold gamma dash. So the test statistics is just an estimate of the variance. This is the variance x square n. So if n is equal to 1, the variance x naught square will be greater than 1 under hypothesis h1, or the mode of x naught greater than gamma dash. This is the mode of x naught is greater than under root gamma dash. So we will decide h1. In this lecture, we have discussed the simple hypothesis testing, means the Neyman-Pearson decision rule. This was the 10th lecture of the lecture series of random processes detection and estimation. In the next series, we will continue the discussion about the Neyman-Pearson testing. Also, we will discuss in the next lecture the maximum likelihood detector, map detector, base risk, and Bayesian estimator. Till then, thanks for listening this lecture. Thank you.